Now let us study about Biot-Savart Law. Okay. So John Baptist Biot and Felix Savart, they discovered a law in which, okay, so if you have a current carrying wire, we take current carrying wire and we take a distance from it. Okay. So what happens is we have to see what's the magnetic field at that point. Okay. So if we keep a compass there, magnetic compass near a wire, we know the compass needle will deflect. Okay. So what is the strength of the magnetic field at that point, that we can find using the Biot-Savart law. Okay, first we'll see a picture there, then we'll go to the statement. Okay, now we'll take a wire like this way. Okay, let's take a wire here, and then we're going to pass current through it. Okay, so we'll connect to a circuit like this way, like this. Okay, this is a negative of cell and this is a positive of the cell. So negative and this is a positive of the cell. Okay, now what we do now, we take a point there. Okay, so let this point be here. Okay, this point is P. What will be the magnetic field at this point P? We must find. Okay, for that we take a small element here. Okay, small element. This element will be dl. Okay, and the distance of this point, okay, P from this small element dl, that is r cap. Okay, that will be the distance here. So there is an angle here. Okay, between this wire and this distance here, that angle is theta. This is a wire here. Now we must see what's the magnetic field at this point here. Okay, so current, first we will see the direction of current. Current goes like this way. Okay, from positive to negative like this way. Now if we calculate and see, the magnetic field at this point P will go into the paper or into the board here. So this will be the direction of the magnetic field B, dB. Okay, so when current passes through wire, we know there's a magnetic field. Okay, so what is the magnetic field at this point P, that we must find. Okay, so let's see a statement now. The magnitude of the magnetic field dB vector at a point P at a distance r from the small elemental length dl taken on a current carrying conductor varies. First one, directly as the strength of current I, dB is proportional to I. Second point, directly as the magnitude of length element dl, dB is proportional to dl vector. Third point, directly as a sine of the angle theta between dl vector and r cap. So dB is proportional to sine theta. Then next one, inversely as a square of the distance r. Okay, so dB is inversely proportional to 1 by r square. Okay, so let's see this now, statement here one by one. So let's see the magnetic field dB, it varies as strength of the current. That means if you send more current there, the magnetic field will be stronger. That's the first one. The second one, as a magnitude of length element dl. So if we are taking a small element here, okay, but you take larger element, the magnetic field also will be larger. Third one, it varies as a sine of the angle. So if the angle is like this way towards 90 degrees, then we will get more stronger magnetic field. If you go here, the magnetic field will become 0. So we'll see that later. Okay, third, our last point here, inversely as square of distance there. Okay, so as you go far away from it, okay, what happens is the magnetic field will decrease as square of the distance here. Okay, r square. So as the distance increases, the magnetic field decreases as a square of the distance. It's an inverse square law. Okay, now let us see, and we'll see the how to write it as in an equation form. Okay, so now let me pause it for a moment. Okay, now I have erased this. Let me come to this part here. Now we see that from the equations. Okay, first one they say the magnetic field is in directly proportional to the current. Okay, that's the first statement. Second statement is the magnetic field is directly proportional to the element length dl. That's the second statement here. Third statement. Okay, third statement right here. Okay, the magnetic field dB is directly proportional to the sine of the angle here, sine theta. Okay, that is third statement here. Then fourth statement, the magnetic field is inversely proportional to the square of the distance. Okay, so we have these four equations now. Okay, so what we do now, we combine all these four. Okay, so let me write here. So combining the equations, so we combine all the equations here. So what we get is the magnetic field dB is directly proportional to I. Okay, then dl also comes directly proportional to dl also. So write dl here. Okay, then sine theta also is there. So sine theta, but we have r square in the denominator. So we have here r square in the denominator here. So the magnetic field is directly proportional to I dl sine theta by r square. Okay, so this is a format here, how to write this. Now what we do now, we have to, or we can take this as a final equation. Okay, one of the equations here. Now what we do, you must remove the proportional sign. Okay, so what we do, we put a equal to sign and a constant here. So dB is equal to constant k into IDL sine theta by r square. Okay, so value of k is mu naught by 4 pi. Okay, that will substitute here. So dB is equal to mu naught by 4 pi, okay, into IDL sine theta by r square. Okay, so now this is in just we see the magnitude of the magnetic field. Okay, now we must see is a vector format. So what we do, so dB vector, okay, is equal to mu naught by 4 pi into I, current is a scalar, okay, but we'll take current element, that is IDL. This thing is taken as together. Okay, so current is going through the element here, so we take current and element together, that will be taken as vector quantity. Okay, so IDL cross r cap. Okay, so r cap is a direction here, shows it, divided by r square. Okay, so this is how to write in vector format. Okay, this is a vector notation. So it's enough that you write up to here, or you write in vector also. So this is very important here. You may ask how the r cap comes. R cap shows the direction so that we get a vector. Okay, so we know that a vector cross b vector is equal to AB sine theta. Okay, you can now understand the format here, IDL sine theta. So instead of that we write as I into DL vector cross r cap. Okay, so r cap is a unit vector which shows the direction. Now we'll see how to show this thing, magnetic field here. Okay, and then what will happen if you have the full element here. Okay, now we'll take the full element here and then we'll see what will happen to the magnetic field. Okay, let me erase this part here. Now let me continue from this. Okay, so you must see the magnetic field to the full element here. So we write as the magnetic field B, okay, is equal to, you must integrate this dB. Okay, integration of dB vector. So integrate this, what we have is, okay, we can take this thing and integrate it. Okay, mu naught by 4 pi is a constant, so we'll take it out. Okay, so what we get is mu naught by 4 pi into integration of I dl. Okay, and in that also I is also a constant here, so we can take I also outside. Okay, dl vector cross r cap by r square. Okay, so this value, this will give us a entire magnetic field. Okay, so let me erase this. And they say that if you hold right hand like this way, okay, we can say the current in, or the, we can express this in 3 dimensions here. So in this case we take this thumb to be the magnetic field dB. Okay, and then this one, okay, this one forefinger is taken as IDL, and this middle finger is taken as r cap. Okay, I'll draw it and show it for you. So we have 3 vectors like this way. Okay, so top one we take it as dB vector, the magnetic field. This side we take it as I into dl. Okay, and this side we take it as r cap. Okay, so these are the ways of expressing it. Now we'll see some special cases there. Okay, let me erase it out. So let us now see the proper definition here. Okay, or this is a formula here. dB is equal to mu naught by 4 pi into IDL sine theta by r square. If you remove this formula, you can easily solve this equations, or any sums that we have. So we'll see some special cases here. Okay, if the point P lies on the conductor, okay, the point P is there now, it goes and lies here. So what happens? The angle theta becomes 0. Okay, so we know sine 0 is equal to how much? It is 0. So the entire thing becomes 0 here. So that's what it is here. So magnetic field, the magnitude of the magnetic field becomes 0. Okay, it's very easy to understand. Second one, you see, if the point P lies perpendicular to the conductor, so the point P is now perpendicular, so angle theta is 90 degrees. So instead of theta, you substitute sine 90. Okay, you substitute 90 degrees, so we get sine 90. Sine 90 value is 1. So we get dB vector is equal to mu naught into IDL by 4 pi into r square into n cap. Okay, so actually this magnitude won't come. Okay. So this will show the this will show the magnetic field there. Okay, so what happens is sine 90 becomes 1 here, and n cap is a unit vector which is perpendicular to both the current and the this one, this is the r cap also. Okay, So next we'll see what are similarities between electric field and magnetic field. Okay, so let me pause it for a moment and rub it out. Now let us study the similarities between electric field, that's from Coulomb's law, and magnetic field from Biot-Savart law. Okay, so let's study this differences or similarities first, then we'll go to differences. So electric and magnetic fields obey inverse square law. Okay, and the long range fields. So let's see this now. So this equation for electric field, it's coming from this one, Coulomb's law. We derived it. Okay, you can refer to the first chapter. So electric field E is equal to 1 by 4 pi epsilon naught into Q by R square into R cap. But if you see Biot-Savart law, B is equal to mu naught by 4 pi ideal sine theta by R square. You can see R square is the denominator. So it obeys the inverse square law. Okay, that's the first point there. Second one, obey the principle of superposition. That means we can add this thing. We learned that total electric field E is equal to E1 plus E2 plus E3. We learned now. Same way, we can also add the magnetic fields. B is equal to B1 plus B2 plus B3. That we can add it. Okay, so we can say that the electric field is proportional to the charge there. Okay, so more is the charge, more is the electric field. The second one, magnetic field is proportional to the ideal, the current element here. Okay, we say current and element we say. So current element ideal. Okay, so more is the current and the length there, so more is the magnetic field. Okay, so these are similarities. Next we'll see what are the differences between electric and magnetic fields. Let us now study the differences between electric field from Coulomb's law and magnetic field from Biot-Savart law. Okay, so first one point here. So it is first point is the serial number, the electric field and magnetic field. First point, produced by scalar source, that is electric charge Q. Okay, so charge Q will give out the electric field, but magnetic field is produced by the vector source here. You can see here current and the element dl. Okay, so current element idl vector. So this is a vector source. You can see vector here Q dl, but for Q we don't have any vectors. Charge is not a vector quantity. Second one, it is directed along the position vector joining the source and the point at which the field is calculated. So suppose you want to find the electric field at this point. This is a positive charge here. So electric field will go in the straight direction only. Okay, it's directed along the position vector. So this will be the position vector here. If you want to write the position vector, you can write as R here. Okay, so this will be the same direction. But if you see for magnetic field, it is directed perpendicular to the position vector R vector and the current element IDL vector. Okay, so now let's see the picture here. So current is going through wire here. This is a current here. This element is DL, and then the distance is R, and you see the magnetic field is going into it. Okay, it's perpendicular. Okay. Now next one you see, third one, it does not depend on angle. Okay, so the electric field does not depend on the angle there. But if you see for magnetic field, say it depends on the angle between the position vector R vector and the current element ideal vector. So you can see there's an angle there. Okay, so we learned now dB is equal to mu naught by 4 pi into ideal sine theta by R square. So sine theta is there. So this angle depends. Okay, so when the angle changes, the magnetic field also will change. Okay, so this is about the Biot-Savart law. Thank you for watching.